Hello, Kev Hopan here again. In the last session, we looked at how to express the results of intervention studies in terms of the differences between groups. We're going to carry on in that vein today. Let's start first of all by looking at the two types of data. Admittedly, there are more, but we'll confine ourselves to these basics. There's categorical and continuous. Categorical data may be patient characteristics such as male or female, or outcomes such as whether somebody suffered a CVA or not. These categorical outcomes are the ones we were looking at in our last session. Continuous data, on the other hand, do not fall into either or groups. They are, as the name suggests, continuous, such things as height, body mass index, blood pressure, and so on. Now, let's imagine we take a continuous variable, which could be body mass index, or perhaps the number of days a patient waits for a surgical operation, and plot that along the x-axis of a graph, and along the y-axis, which seems to be missing here, the number of people who have a particular BMI or who have been waiting a particular number of days. You will recognize this perhaps as what is referred to as the bell-shaped curve or the normal distribution. You will see that here in the middle is the average or mean. It could, for example, be the average number of days people have been waiting, and you can see that the vast majority of people have been waiting for the average. But around this, there is a distribution. Now, we can express this mean in numerical terms. You all know how to work out an average. But would it not be good if we could somehow find a number that could explain how much spread there is around that mean? For example, supposing, in addition to the mean, we could take an interval and say that most of the measurements lie within that interval. Typically, we choose 95%, which means that between that lower limit and upper limit, 95% of all measurements of waiting times for surgery will fall, leaving a lower 2.5% and an upper 2.5% that is at either end. So, how do we calculate this interval? We use something called the standard deviation, and you'll be pleased to know you don't need to know how to work it out. Just bear in mind that it takes account of the mean, the variation of all the measurements from the mean, and the number of measurements, or patients in this case, in the study. There's a marvellous property the standard deviation has. If you multiply it by 2 and take that number away from the mean and add that number to the mean, in between those two limits is the 95% interval containing all those observations. Now, what do you think would happen if we repeated a test again and again? Supposing, for example, we measured the BMI in this top group, and then we measured it in a different group and in a different group. Can you see what's been happening? In this group, that was the mean, and that was the dispersion or spread. In this group, that was the mean, and in that group, the mean. In other words, when we do repeated tests, we don't get the same results. We get a variation in the means. Now, if we plotted all these means on a graph, we would end up with another normal distribution or bell-shaped curve, like this. And this time, what we're going to talk about is something called the confidence interval. We don't want to repeat the study an infinite number of times. What we want to do is calculate what the confidence interval would be from a single study. And the way we do that is by using something called the SEM, or standard error of the mean. So from a single study, we can calculate what the standard error of the mean would be And what this translates to is the following. So let's talk about how the confidence interval can be of value to us from a single piece of research. Let's go back again to looking at body mass index. Say we have measured the BMI of a sample of pupils at the medical school here in the University of Nicosia. Now that sample will give us an estimate of the BMI of the whole of the student population, but it won't be the exact mean of the BMI. We can, however, calculate a confidence interval around that mean, and that confidence interval can be used to tell us how precise the estimate of the sample is compared to the true value of the whole population of students. The confidence interval, if you remember, spans the lower and upper confidence limits of 2.5% at the low end and the upper above the 97.5% limit. We could say that the estimate of the BMI from our sample of students from the University of Nicosia would give us a confidence interval such that the true BMI would have a 95% chance of lying between the lower and upper limits. This isn't strictly statistically true, but it's good enough for clinicians like you and me. So just to recap, if we've calculated the mean from a sample and used that to calculate the confidence interval, we can say that the true mean, the true value, has a 95% chance of lying between the upper and the lower limits. Now, let's turn to the subject of when we compare continuous data. Suppose, for example, that we take a group of obese patients and we give them an active drug for losing weight, such as orlistat, and we to one group, and to another group or another sample, we give placebo. We measure their weights before and after a certain period of time. We then plot those weight losses, that is to say, how much weight they've lost over the period of time, on a graph, here shown by the x-axis. So this could be, for example, the orlistat group with its mean there, and this would be the placebo group. And notice that the mean loss in orlistat is greater than the placebo loss. We can actually measure that difference. Now we can take that difference and calculate a confidence interval for it, just as we could use a confidence interval calculation from studies of continuous data themselves. Because if you remember, the difference in means, if we repeated the test again and again, would also be a normal distribution. So how does this help us? Well, let's go back to where we started. In an intervention trial, we give one group an exposure and the other group acts as control or a comparison group. We like to measure the difference between the events, between the measurements. That difference is an estimate and an effect size. And we can get an estimate of the true value of the effect size through the confidence interval. Okay, now you may wish to pause here before we go on to talk about the p-value and statistical significance. I want you to imagine that you and I are playing a game with a coin. You must know this, where somebody tosses a coin into the air and asks you which side comes down, shows face up, whether it's the heads or the tails, as you say in English. Okay, now if I threw a coin in the air, what is the chance that I would get a head or a tail? It's half, isn't it? Half and half, or 50%. So half the time I would get heads and half the time I would get tails. This would hold true if I did it many, many times. If I threw the coin and got 2 heads in a row, you and I would probably think that that was not unusual. It would still be possible for us to accept that it arose by chance. Now, the probability of that happening is not 1 in 2, not half, but now 1 in 4, a quarter, 25%. Now, supposing I threw a coin up into the air 3 times and it came down heads every time, again, that could still arise by chance, couldn't it? It would now be 1 in 8. If I continued to throw a coin and it came down heads every time, or tails every time, after a while we just might think there was something wrong with the coin. And if money was involved and we were gambling on this game, I think that after a few throws, somebody would certainly get suspicious. Now, what is the p-value? The p-value is the probability of something happening. That's what, okay? Now, in research, we say that p-value is the likelihood, or that's to say the probability or chance, that an effect could have arisen purely by chance alone. By convention, we say that when the p-value is low enough, chance was not at play, that there was a cause and effect relationship between the intervention that we gave and the effect size that we saw in the study. And when that happens, we say it was statistically significant. In other words, statistically, it was so unlikely, rather like we wouldn't believe somebody a gambler who managed to throw 6 heads in a row. We wouldn't believe that. We'd say that we say we don't believe that this was pure chance. It was statistically significant, so unlikely. Now, usually we take p as being less than 0.05, not 0/05, as shown there. And I'm sure you all spotted that deliberate mistake. The p-value measures the strength of evidence against the null hypothesis. Now, you might have forgotten what that means from medical school days, but the null hypothesis is a kind of way of saying at the beginning of a study that there is no cause and effect relationship between the intervention we're giving and what we see happen. Okay? And if the p-value is really low, we say the null hypothesis was wrong. In other words, there was a cause and effect. And the lower the p, the stronger the evidence. There's been a lot to take in there, and there is quite a lot more, which you'll find in your course book. For now, let's just turn to categorical data. If you remember, we started at the beginning by saying there were 2 types of data, categorical and continuous. Categorical data, you will remember, we report as event rates. And when we compare control groups and treatment groups, we look at the difference between the event rates in both groups. Then the difference between the 2 rates, CER and EER, if you remember, which stand for comparison event rate or control event rate on the one hand, and exposed event rate or experimental event rate on the other, is an estimate. And like all estimates, we can calculate a confidence interval around such things as the risk difference. So let's just recap what we mean. Clinical significance refers to the size of the effect. Statistical significance refers to how likely an effect could have arisen purely by chance alone. Confidence intervals can give us an idea of how precise the treatment effect is from a particular study. Confidence intervals can be calculated for all summary statistics like risk ratio, risk difference, RRR, number needed to treat, and when we come to talk about diagnosis, such things as sensitivity, specificity, etc. Okay, now there has been an awful lot to take in here. I won't be surprised if you need to play this back again. You will find a lot more explanation in chapter 2 of your course book. And it would be good if you could practice the summary statistics in the Ramipril study up on Moodle. Thank you.